So welcome everyone. I hope you can hear me. Welcome to this first lecture of the ECCB seminars on chemical bonding. I am Ángel Martín Pendas, and I'm the current president of the committee from the University of Oviedo, Spain. So let me briefly introduce the committee to those of you who are new to this community. The European Committee for Chemical Bonding is a non-profit society dedicated to advancing the science and research of chemical bonding theory in Europe. It serves as a hub for researchers, academics, and professionals in the field. Among its missions, we want to organize conferences. We have a biannual conference, the European Symposium on Chemical Bonding, called CBOND, that awards prizes and scholarships for groundbreaking research, publish special issues in scientific journals devoted to significant contributions in chemical bonding, and so on. If you are interested, please visit our website. After the Zoom lecture, there will be a 15-minute session or 10-15-minute session dedicated to questions. And we invite you to raise your virtual hand so that we as organizers will unmute you and in turn so that you can ask your questions directly. If you intend to ask a question, please prepare a concise wording in advance. Our lecturer today is Professor Martin Head-Gordon, one of the leading figures in theoretical and computational chemistry. He was born in Canberra. He completed his bachelor and master's degrees at Monash University in Melbourne. And then he moved to the US, where he obtained his PhD in 1989 in theoretical chemistry at Carnegie Mellon University, working with Sir John Popple on molecular orbital theory and algorithms. From 1989 to 92, Martin was a postdoctoral fellow at AT&T Bell Labs, working with John Tolley. Then he joined the Berkely faculty in 1992, where he is now the Kenneth Pitzer Distinguished Professor in Chemistry. And he's also a faculty scientist at Lawrence Berkeley National Lab, where his group continues to develop the next generation of quantum chemical methods. Martin's research focuses on many different topics, developing new and more efficient ways to describe electronic structure, with contributions that span both wave function theory and also density functional theory. He and his collaborators have designed many innovative approximate coupled cluster and local correlation methods, making accurate quantum mechanical calculations feasible for much larger systems than before. He's also behind several widely used density functionals, which have become standards in computational chemistry. Beyond methodology, Martin's work has shed light on problems ranging from catalysis and spectroscopy to intermolecular interactions and chemical bonding, and always guided by a deep intuition for what's physically meaningful and computationally practical. He's a fellow of the American Academy of Arts and Sciences, the American Chemical Society, the US National Academy of Sciences, or the Royal Society of Chemistry, and has received and has recently become the new president of the World Association of Theoretical and Computational Chemists. He has trained a large number of students and postdocs who now lead their own research groups, and he has received many recognitions like the Medal of the International Academy of Quantum Molecular Sciences in 1998 or the Schrödinger Medal of the Watt Association in 2020. In short, Martin Head-Gordon has not only expanded the theoretical toolbox of chemistry, he has also helped define what computational chemistry looks like today. Without much further ado, please join me in welcoming Professor Martin Head-Gordon. The stage is yours, of course.
Thank you, Angel. Can you hear me okay?
Yes, perfect.
Excellent. Well, firstly, thank you for the very, very kind introduction, maybe even too kind. So let me try to be honest. I originally began working on energy decomposition analysis because I thought I was maybe an average chemist, and I wanted to kind of understand more. And so from a theoretical chemistry point of view, it's then nice to do it. So what I thought I would talk today about is non-bonded interactions, and this is kind of actually the groundwork by which we also think about chemical bonding. But one can't really talk about one without doing the other first. So I thought we would focus on non-bonded interactions and see how we go. So I will give some general introduction. We'll then talk about a variational framework for understanding non-bonded interactions. The same framework applies to bonded interactions if we wish, but again, there's not enough time to do it all today. Then we'll talk about analyzing charge transfer between molecules and polarization induced in one molecule by another. And then we'll finish up with some comparisons and controversies and conclusions, just to really let everyone know that this is a dynamic area not fully settled. All right, now, as Angel said, I was born in Canberra. If you're not used to looking at the world from an Australian perspective, here it is. There's Canberra up the top there, roughly in the center, and then after that, my family moved me to Canada. So I spent ages 6 to 13 in Nova Scotia over there, and then after that, despite the best advice of my brother and me, who wanted to stay in Canada, they moved us back to Australia. Then I went to the US to study for a PhD, and then I've been at Berkeley since '92, and I like software development very much. But of course, one of the ironies of becoming a professor is you don't have the time to do it yourself. You have instead the time to try to meet people who do it with you. And my research interests Angel summarized nicely. Okay, well, computers are the instrument by which we do things, and it's maybe just interesting to reflect briefly on where we are in 2025. We are in the era of exaflop computing. The mustardy triangles here is the world's number one, the number of adds and multiplies per second done by the world's number one supercomputer as a function of year, and we're in the exaflop era. El Capitan is unfortunately a defense-related computer, so no scientists doing unclassified research can get access to it. But more encouragingly, a 2025 server offers roughly the compute performance of the world's number one supercomputer just around the millennium. Okay, so EDA, what is it? Well, we might begin by conceding that normal electronic structure calculations are numerical experiments. In other words, you begin by combining virtual beakers of nuclei, for instance, in the case of making the water dimer, protons and oxygen nuclei, and mix in electrons, and then you make the final product. By contrast with the gigantic energy changes associated with that, and again, if you've looked at the outputs of electronic structure codes, you know the magnitudes of energies are enormous because the electrons, especially the inner shell electrons, are so strongly bound to their nuclei. But that's really not relevant for chemical energy changes. So the goal of an EDA is to try and seek small energy changes in steps that begin from an appropriate reference state. So the same way that you then subtract the total energy of the water dimer from twice the total energy of the hydrogen of the water molecule to get the hydrogen bond strength, one would like an EDA to do these steps in even more fine-grained a way, to reveal the physical and chemical drivers of the interaction, in this case, the hydrogen bond. And to keep the chemistry simple, most of this talk will focus on looking at the hydrogen bond through this lens of energy decomposition analysis. And we must then concede that EDA results depend on the reference state. For instance, if I wish to analyze the interaction between lithium and fluorine, I will get a much different picture if I begin from ionic products, as would be appropriate in solution, versus neutral atoms, as would be appropriate in the gas phase. They're also even further non-unique given a reference state. If you kind of think, well, the initial state is kind of a thermodynamically well-defined configuration of non-interacting fragments, and the final state is then also thermodynamically well-defined. The pathway by which you join them is non-unique. So those are the kind of things that you might and perhaps should feel a little skeptical about when you think about energy decomposition analysis. And those demerits, those difficulties, should be weighed up against the potential benefit of trying to make a bridge to the language of chemistry and to chemical concepts and to see whether they can emerge from reasonably well-defined, even though not unique theory. And one might contrast EDA, where one's trying to get energy contributions, with associative analysis methods, where you try to look for correlations between a suitable descriptor. And here are some common descriptors: the electron localization function, atoms and molecules descriptions, the non-covalent indicator, sigma and pi holes, and so forth. All right, well, I'm going to jump. Most of you should be reasonably well versed in quantum chemistry, but I will work within the framework of density functional theory, where we model the electron density. We know that it's a formally well-founded theory built on the famous Hohenberg-Kohn theorems that say that we don't actually need the wave function to get the ground state. Rather, we can attempt to model an unknown exchange correlation functional in red with exactly known contributions from kinetic energy, electron nuclear attraction, and classical electron-electron repulsions. And we try to balance accuracy against feasibility in DFT. And this famous Jacob's ladder of functionals, which we owe to John Purdue, as a way to classify. And from the chemistry point of view, we will be on rung 4 today. We will be using hybrid density functional theory because this is reasonably accurate, quite well established, and one should make choices on those grounds. And so this is a quick summary from the work of Stefan Grimmer's group in Bonn, showing you the practical performance. On the y-axis is the weighted mean absolute error. On the x-axis is functionals grouped by ascending rung from right to left. The local density approximation is not shown, so rung 1 is off the scale in terms of a giant error that would be, well, 1 or 2 laptops above what you're staring at now. But then you can see that by the time you get to rung 4, you're getting down to something that, in terms of a weighted mean absolute deviation, is not too far off chemical accuracy. You still need some error cancellation to achieve useful results, but we will largely be using range-separated hybrids and doing things that way. Okay, so DFT is our toolbox. DFT then is the numerical experiment, which we will accept as ground truth and try to analyze. Now, what kind of contributions need to be in the analysis? Well, there should be some coming from long range and some from short range, and you can look up in a textbook what the long range ones should be. There should be electrostatics. There should be induced electrostatics or polarization. So this is cartooned here by the charge distributions changing. And these have well-known power laws. So again, if we're looking to build and assess a theory, we can ask, do we get the power laws right, for instance? And then finally, there is dispersion. So these are the textbook long-range interactions. And then there are short-range ones that also are textbook and have exponential dependence with distance. In other words, why they're short range is because they decay exponentially. Pauli repulsion, your intuition should be the forced introduction of wiggles or nodes in the wave function due to satisfying the Pauli principle and making sure each level is only singly occupied. And then finally, charge transfer, which is the HOMO-LUMO interactions, the HOMO of one fragment interacting with the LUMO of the other, frontier orbital type interactions, also exponential with distance. So these are the things we need to capture. And in that light, you can ask, what is the hydrogen bond exactly anyway? And so someone who's driven by observables would say, oh, it's the 20 kilojoule per mole interaction between two water molecules characterized by roughly a linear OHO geometry and a 1.9 angstrom separation between the donor proton and the acceptor oxygen. So that's kind of easy, but people do still in 2025 debate the origin. because you could say that it is permanent induced and induced electrostatics. That's sort of implicit in classical force fields. But we might note that the dipole moments of the two water molecules are not optimally aligned. So clearly this is a contributor, but it cannot be the only thing. And so at a minimum, you would need Pauli repulsion as well. And then at the other extreme is the possibility that charge transfer is actually quite important, and that this is a weak example of a donor-acceptor interaction, similar to what we would find familiar from inorganic chemistry for metal-ligand interactions. So in that language, this would be an N, a non-bonding orbital on oxygen, donates to sigma star, the OH sigma star orbital dative interaction. And spectroscopically, there's some evidence for that. There's a red shift on the order of 70 wave numbers, kind of small though. And you might wonder what would happen to the effect of polarization, this molecule by that molecule and vice versa. Wouldn't that also maybe induce a red shift? So we need to look into those things and try to understand. So in principle, that's what our EDA should do. Okay, so we've got these contributions. The ones that exist at long range are out of the textbook and are properly, and any half decent EDA should get them right. The other ones are more non-unique because they have the same distance dependence. They occur in the same range. So the interaction between filled orbitals on one fragment with filled on the other, filled on one, empty on the other, these coexist. We've got to define them nicely. And then finally, bonding interactions. If we want to extend this to chemical bonding, then there will be the delocalization due to overlap. So one would lastly have to do that. Okay, what about some history? Let's put all this in context. While it goes back further, a seminal piece of work is by the Japanese group Kitara and Murakuma. They developed what nowadays is known as the Kitara-Murakuma EDA for Hartree-Fock theory, which is a primitive form of density functional theory, in 1976. It was then translated, adapted, slightly generalized by the late Tom Ziegler and R.V. Rauch just a year or two later. And nowadays, the Ziegler-Rauch EDA, slightly generalized and converted in terms of NOCVs, is widely used in the ADF code, amongst others. Natural bond orbital analysis arose in the late 1980s due to the work of Frank Weinhold and others, and is widely used. And then another method that really one should be aware of is symmetry-adapted perturbation theory, which differs from what I'm doing today and these methods there, in the sense that this is a theory that predicts the intermolecular interaction in addition to providing values for its components. So this is kind of a nice contrast, actually, and arose from the Polish school of quantum chemistry. The name most prominently associated with it is Krzysztof Celiewicz. And then most closely related to what I'm talking about today is work that was initiated by Sigrid Peiermoff, Jiali Gao, and Yurong Mo in the year 2000, and inadvertently reinvented by me and my group in 2007. And you can ask me the story about this if you would like. And then I would also mention that that DFT-based EDAs have been attempted, EDAs based directly on the density. Okay, so that's some context, and the green box is more or less the takeoff point for what I will describe here in part 2, which is the variational energy decomposition for non-bonded interactions. And if you want to read about it, our effort to write a review on this was in Annual Reviews of Physical Chemistry in 2021, and these are 2 of the source papers. All right, so this is then going to be a case of density functional theory done with constraints. If you're familiar with constrained DFT, this is somewhat similar, except that our constraints will be in Hilbert space. And this is limited to single determinant wave functions of the SCF type, so Kohn-Sham density functional theory, including, if we had it, the exact functional. we split the interaction energy into a preparation energy, a frozen energy, a polarization energy, and a charge transfer. These are all the energy changes as we go from monomers to complexes. And the preparation energy is then largely the energy cost required to distort an isolated molecule from its favorite isolated molecule geometry to its complex geometry. But if we're doing a radical or a chemical bond, there may be electronic distortion as well. That's part of the preparation energy. Then the frozen energy is to make the simplest possible trial function. And the constraint on the trial function is that the orbitals are not allowed to relax from their monomer form that's used to evaluate the preparation energy. Instead, the only thing we do is the minimal deformation necessary to satisfy the Pauli principle. And so this frozen energy is the crudest variational trial function you can imagine, but it has the physical significance of including permanent electrostatics, dispersion, and Pauli repulsion as a package. So the good thing is that this is a very well-defined, very cleanly defined energy. It doesn't rely on any basis representation. It's defined for any functional. It's a very natural starting point. So I feel quite comfortable with this. The only thing to feel slightly uncomfortable about is that it contains not one physical driving force for the strength of a complex, but three. One that could be attractive or repulsive, one that's definitely attractive, and one that's definitely repulsive. Okay, well, then comes a limited release of the constraints, and the limited release of the unrelaxed orbital constraint is to allow relaxation in green with the constraint of only being on fragment in red. And that is called SCF for molecular interactions. It has a long history, actually, going back to circa 1980 or so. You could imagine doing the on-fragment relaxation, and this is the way, in fact, we first did it, with mixing of the fragment occupieds that we get from the frozen energy with the atomic orbitals that span a fragment virtual space. So we could do that. But that's a little awkward because that begins to rely on atomic orbitals. What if our basis set was plane waves, for instance? Or what if we wanted to do finite elements? It seems not good to have an EDA that depends on the underlying representation. So instead, we use a representation independent form of virtuals that we call fragment electric response functions, or FERFs. And the FERFs are the exact linear response of the occupied orbitals to a uniform electric field or a field gradient. And if you want some feeling for that, think about a hydrogen atom in its ground state described by an s orbital, and then apply an electric field, say along this axis, the x-axis, let's say, and ask, what is the linear response of the hydrogen of the 1s orbit? Well, the answer is it should polarize in the direction favorable to the field. And what does that polarization look like? It looks like a little shift of the S function off center in the direction that electrons wish to move towards the positive pole of the field. Okay, so like this. And what kind of a change is that? Well, that little translation of an S function, that's exactly a P function. So in fact, the polarization specific virtuals, there'll be one for each occupied orbital. And crudely speaking, for the S function, you'll then get a set of three dipolar FERFs, the three P functions that are the linear response to the X, Y, and Z fields. And then if we were looking at the field gradient, we would get five responses that are D-like functions, and that generalizes to then more complex situations, such as the molecular orbitals in a molecule. Then finally, we release the constraint of only on-fragment relaxation. So this is minimizing the SCF energy with that constraint on orbital mixing to finally allow electron flow and to then see donor-acceptor interactions. And at the end of all that, you then get a sort of an answer to the question of what is the hydrogen bond and what's its origin, because we get a kind of a fingerprint of the hydrogen bond in terms of these 4 energy changes. There's a preparation, and these are in kilojoules per mole, and this is done, if I remember right, with omega B97M-V in a quadruple zeta basis set. We can work right at the basis set limit with these FERFs, which is nice. And you can see that the 20 kilojoule per mole interaction energy is roughly half coming from the frozen term. Preparation is free. In this case, there's little deformation. Then polarization is about 1/4 of it, and charge transfer is roughly 1/3 of it. So really, this fingerprint is saying that it's not just one thing. It's really a synergy of different interactions. There is clearly some attractive electrostatics as part of this frozen interaction, but that's not all. And the strength of the interaction slightly more than doubles if you include the other 2 contributions. So kind of a fingerprint. All right, just a little more about about these constraint calculations. So if you think about the Hilbert space of let's take a 4-fragment system, fragment A, fragment B, C, D, for instance, the water tetramer, say. Well, what we're doing in the frozen energy is just doing optimization on each fragment in isolation. So this should be intuitive. We're just kind of concatenating the orbitals. And then we variationally evaluate that energy. Then I've already told you this in detail, but sometimes it's good to hear it twice. So what we do with polarization is we use what is called the dipolar quadrupolar FERF basis. So the dipolar basis is the 3 polarization functions for each occupied orbital associated with a uniform field. And the quadrupolar responses come from the field gradient and gives us 5 extra functions for frozen orbitals. And so that's how we do that. And then we put it all, and then the charge transfer bit is just a subtraction. Well, I'll show you in a little bit how you can do it in a fancier way to get more insight. But if you just want the number, what is the total charge transfer energy? You just get it by subtraction. So the point is that we have the initial energy of the isolated fragments, the frozen energy, the polarization energy, and the final fully relaxed energy. We do subtractions, and that gives us the deltas. So in summary, what have we done? We've got a theory that isolates the driving forces into 3 terms. There's the frozen term, which itself contains 3 driving forces. There's the polarization energy lowering that we claim nicely separates out the induced electrostatics. And there is the charge transfer term that then should be donor-acceptor interaction. So this is the same cartoon I had before, but now indicating how they're lumped into these 3 energies. And if you can do the energy, you can do the force. So you could just differentiate those terms and get a force decomposition. You have preparation forces, you have frozen forces, you have polarization forces, and finally, you've got charge transfer forces. And it's sort of easy to say this, and some of these terms are easy to do. The preparation force is trivial. The frozen force was notably difficult to do, and this was done by Yueji Mao and Abdul Al-Dasari. And the polarization force is fairly easy because that's a trial function that was variationally optimized. And then you get nice pictures like this. So let me walk you through what the force decomposition analysis looks like for the complex between water and chloride. And we could first look at what we should look at here. Let's look at the proton donor chloride distance. Okay, which is this one here. And the first thing you can see is that there are 3 forces that drive towards shortening the proton donor chloride distance. There is an electrostatic force, there is a polarization force, and there is the charge transfer force. And then opposing that is the Pauli repulsion or van der Waals. And remember, this van der Waals and this electrostatics are both put together in the frozen force, which we then decompose on the assumption of classical electrostatics. So this is force balance. That force adds to 0. And you can see that everything wants to shorten this distance except Pauli repulsion, which is that inducing nodes in a wave function is the price we pay for enjoying electrostatics, polarization, and charge transfer. Then we could look at the oxygen proton donor distance, this OHD distance. And here, well, the first thing that should strike you is that this is not a force balance. So what did I do when I ran the job? Or should I say, what did Abdul do when he ran the job? Well, what Abdul did was he took an optimal monomer geometry for water and then optimized the chloride position against that. And so this force imbalance is actually quite interesting. It says that everything wants to elongate that bond. Electrostatics wants to elongate it. Pauli repulsion, van der Waals wants to elongate it. Induction wants to elongate it. And donor-acceptor interactions most want to elongate it. And that should make sense because the donor-acceptor interaction will be lone pair on chloride donating into anti-bonding orbital here. So the force imbalance is quite, gives us nice insight. And okay, so that's all I want to say about that one. Then if you've started thinking about forces, it then becomes natural to think about trying to move on the constrained potential energy surfaces defined by the frozen energy and the polarized energy. And that makes one realize that the EDA, as I have explained it so far, could be characterized and really should be characterized as a vertical EDA. In other words, it's the vertical energy changes at a single geometry. And the stronger your interaction, the bigger the repulsive and attractive terms. And that can be a little awkward. And maybe it's good to think about an alternative picture where you try to get the optimal geometry on each surface. Picture's worth 1,000 words here. So the vertical EDA is the dashed line at the optimal complex geometry. There is the polarized energy. There is the frozen energy. And then we could contrast that with saying, well, instead of doing vertical, why don't I relax on the frozen surface to find the optimal frozen geometry and relax on the polarized surface to find the optimal polarized geometry, and then relax finally without constraints. And that should tell me the driving force for structural changes in the complex in terms of driving forces from the frozen, the polarization, and the charge transfer. So this is an alternative picture. One is not more right than the other or more wrong than the other. It's just that in some scenarios, it can be natural to try and look for smaller energy increments, and the adiabatic picture would give you smaller ones. So that's kind of appealing. And as I already stated, the adiabatic increments will allow us to see changes like how complex the structure of a molecular complex evolves as you go from frozen to polarized to full, or how the vibrational frequencies either on a monomer or between monomers evolve. And to implement it, again, you need the gradient. And so there's the fingerprint I showed you before for the vertical EDA of the hydrogen bond. What about the fingerprint for the adiabatic EDA? Well, here it is. And maybe not surprisingly, the frozen interaction becomes stronger. In other words, the adiabatic fingerprint places a much bigger emphasis on the energy lowering associated with the frozen interaction. And like meat in the sandwich, the polarization energy lowering is now almost halved, and the charge transfer energy lowering is reduced by about 1/3. So this is two different ways of looking at the same thing. Again, it's a bit like the blind man poking the elephant. The elephant is the hydrogen bond. The blind man or blind person is us trying to design EDAs, and we can design two of them. And they're each equally valid descriptions of the elephant, the hydrogen bond. What about the observables? This was the thing that was most exciting to me when we first did this. If you look at the optimized geometry of the complex with the constraint of frozen orbitals, monomer orbitals, unrelaxed orbitals, look at this. The OHO distance is linear virtually. In other words, it doesn't change. more than half a degree against the final structure. So we could say that in the water dimer, the linearity of the hydrogen bond is largely a byproduct of the interplay between permanent electrostatics, dispersion, and Pauli repulsion, the three physical driving forces that are contained in this term. So whatever the effect of polarization, it's not structural in the sense of the linearity or lack of linearity, and likewise for charge transfer. So that's super interesting. That's kind of in corroboration of the sigma hole picture, where you look at the electrostatic potential of an isolated monomer to try and infer information about the dimer. All right, now if I look at the proton donor oxygen of the other molecule distance, you see that polarization does have an effect. It shortens that distance by about 1/10 of an angstrom. And then charge transfer shortens it by about 2/10 of an angstrom. So the greater structural effect is due to charge transfer, but you can see an effect due to polarization. Vibrations are super interesting. If we look at the omega-9, which is the vibration of this oxygen proton donor hydrogen, it scarcely changes on going from the frozen to the polarized level of theory, and then jumps by roughly 100 wave numbers when you introduce charge transfer. So this split between the symmetric and between this localized mode and this other mode essentially is largely an outgrowth of charge transfer. So we're in the process of seeing that the HOMO-LUMO interaction has a spectroscopic fingerprint, which is the red shift of the proton donor oxygen stretch. So that's cool. We can do it with continuum solvation. The thing to be aware of is that one should really solvate each intermediate state to be consistent with the idea of variational energy decomposition. Solvation is integral to each component. If we wish to think about the formation of a complex in continuum solvent, we shouldn't just solvate at the end. We should solvate the fragments to begin with. We should solvate the frozen state. We should solvate the polarized state, and we should solvate the final state. And that was the key theory innovation here. Gives a solvation correction for each term and gives solvent-containing contributions to the final interaction energy. And if you want to try EDA yourself using QChem, you can do it at zero cost and nearly zero effort. You've got to download a GUI from iqmol.org, build a complex, for instance, the chloride water complex in iqmol, make a QChem input file, not too difficult. So this is the net charge and net spin of the complex. Here's the first fragment, a chloride anion. Here's the second fragment, a water molecule. Your job type is EDA. What I've been describing here is the second generation EDA. So this is EDA2. And the functional I've been telling you about is omega B97M-V, and then please use a good basis set. And you can run it on QChem server. There's a 10-minute limit, but this will fit. And then finally, you get the output, which is the fingerprint I've been telling you. So we've built this into software, and the software is not difficult to use. All right, so now let's switch gears. Well, let's dive deeper into charge transfer and polarization. And this is the thesis work of Steve Shen, Hengyuan Shen, a current student in my group, with help from Srimuk Guerji and Zhen Ling. And as part of foreshadowing controversies, let me quote Tim Clark, who in 2017 wrote, "There is no reason to introduce a distinction between polarization and charge transfer in weak interactions. We should save our effort for more meaningful pursuits." So I apologize for telling you about something that might be viewed as meaningless according to this quote, but I will try to argue why it is meaningful. Okay, what's the theory? The theory is built on line integrals. So we're going to imagine a first state, for instance, the polarized state. We're going to do charge transfer first. and then a final state that's the full state. And we're going to have a variable, lambda, which when it's equal to 0 will put us in the polarized state. And when it's equal to 1 will put us in the final fully relaxed state. And the path is parametrized by the generators of a unitary transformation, x. And so we're then going to follow the line where x is switched on with magnitude 0 to magnitude 1. And so we can then do the line integral. And the result is quite beautiful and fully rigorous, which is that energy change due to charge transfer that we previously got by subtraction can identically and equivalently be obtained as the trace of a Fock matrix with X, the generator of the unitary transformation, where the Fock matrix is actually the line integral along lambda of the Fock operator at each value along the line. So in practice, we do this as a numerical quadrature with roughly half a dozen quadrature points. And some beautiful things arise as a result of this form. This is a matrix, and it can be indexed by donor and acceptor orbitals, as can this generator of the unitary transformation. So this is an exactly pairwise additive expression for delta E. There's a sister theory for delta Q that likewise is exactly pairwise additive and gives you the number of electrons transferred. You can singular value decompose this generator of the unitary transformation, and that will give you donor and acceptor orbitals. The left, for instance, X connects virtuals to occupieds, so the left eigenvectors would then be the virtuals, the right would be the occupieds. And so this basically says that X can be deconstructed in terms of its singular values and the occupied and virtual orbitals that they connect. And if we get lucky, maybe only one or two singular values or orbital pairs will be significant. And in that case, we will turn our value for charge transfer into an orbital interaction described by the most significant donor orbital and the most significant acceptor orbital. And maybe there'll be two or maybe three. That'll give us insight. And so then finally we can put it all together and then add up the contributions from each singular value. So in other words, that delta ECT here can be exactly re-expressed in terms of the singular value contributions, and so can delta QCT. And so then if we go to water, back to the water dimer, we get fresh insight into CT, and I really like this. So here is the proton donor hydrogen, and in bold is the most important at the level of 90% of the CT, the most important donor orbital, and it's not surprisingly looking like a lone pair orbital on the Lewis basic oxygen. And there's the acceptor orbital, which is looking beautifully like a sigma star orbital. And it's important to emphasize this is not a cartoon. This is the visualization of our exact analysis of the intermolecular interaction. 7 kilojoules per mole, or 90% of the CT interaction, comes from the textbook cartoon. And by the way, how many electrons? 3 millielectrons, 0.003 electrons are donated into the antibonding orbital. So 99.7% of the lone pair stays on the original oxygen, and 0.003 electrons move. Very interesting. And finally, one more important thing is that the phase is significant. We have developed a phase convention, and if the color of the donor and acceptor orbital phases is the same, we get constructive interference between the donor and acceptor orbital, i.e. we get bonding character. So this is telling you the bonding character of the charge transfer interaction in the water dimer. It's only 7 kilojoules per mole, but it is unmistakably a 1/3 part of the hydrogen bond. And now we have come all the way from defining the energy components to now actually isolating without any assumptions the donor and acceptor orbitals. Okay, I will run through this kind of quickly. You can pick more chemical examples. So this is an effort at a slightly more chemical example. So this is the transition state of the Diels-Alder cycloaddition between butadiene and ethene. And so we're looking at this concerted transition structure. And what we will see is that there are two significant complementary occupied virtual orbital pairs. That's a clunky way of saying two significant singular values, two significant pairs of donor and acceptor orbitals. And let's have a look. And when you look at the pictures, look for partial bond formation. Remember the phase convention that I just explained. So here is 49% of the charge transfer interaction between the diene and the dienophile at the transition structure. And now you'll see things are much stronger than in the hydrogen bond and the water diamond. This is 85 kilojoules per mole, and 0.15 of an electron moves in the process of making the transition structure. Well, we're making new single bonds. So this is still a fairly early transition structure in the sense that 0.15 of an electron has moved. Look at the constructive interference that comes out from the analysis. You can see the new single bonds being formed, and then you can see weakening of what used to be the old double bonds, because that's anti-bonding character in the diene. Okay, really nice. And here is the other 49%, which is now in reverse. So this was charge transfer from the alkene to the diene, and this is charge transfer from the diene to the alkene. And they're almost exactly balanced, 85 kilojoules per mole versus 80, forwards and reverse. And look at this, it's also making the two new single bonds. And in this case, it is then depleting the double bonds of the diene and weakening what used to be the double bond of the alkene, and 0.14 electrons transfers. All right, well, having walked through that kind of slowly and carefully, polarization can be done the same way. There's some interesting twists in the derivation. It's a quite beautiful derivation, but we can link the frozen state as a lambda equals 0 to a polarized state, lambda equals 1, and then have the generators of the unitary transformation that carries us along this line yield us a line integral in exactly the same way that I showed you for charge transfer. But now there will be a polarization-specific Fock matrix that's done by numerical quadrature along the line. And then there is a different unitary transformation, so a different X matrix, but everything else is the same. Well, no, it isn't actually. Remember that the variations in X pol are only on a fragment. It's constrained to vary the orbitals only on a fragment. So that means the polarization energy is fragment additive, not pairwise additive. So this is an effective one-body theory. You shouldn't think of polarization as one body, but this analysis gives us a directly additive sum of fragment contributions for both delta E and delta Q. And it's the natural form that comes out of this theory. So singular value decomposition gives then donor and acceptor orbitals on each fragment, one by one. And again, we can look and see how many singular values are significant and how much charge flows. And we can go back to the water dimer one more time and finish my characterization of its hydrogen bond. So here is the leading contribution to polarization. It is 61% of the polarization energy lowering, and it is occurring on the Lewis base. And what is going on here is the lone pair orbital of the Lewis base that is oriented towards the acceptor. And remember the phase convention, it applies here too. It's polarizing towards the proton donor. So it's polarizing in a way that will, if you like, prime it for the subsequent charge transfer. Is it big? in terms of electrons, it's 1.5 millielectrons, 0.0015 electrons are promoted from this orbital into that orbital. So that's 60%. Then there's another 20% that is quite interesting. This is polarization on the Lewis acid fragment. And it is largely the sigma bond, the OH sigma bond. And remember the phase convention. This is destructive interference now. So here's the virtual. So what is, and you can see the node in the virtual if you look carefully there. So this is sigma to sigma star polarization on the Lewis acid fragment, good for 1 kilojoule per mole and 0.7 millielectrons. And then there are even tinier contributions. Remember the singular values, if we look at them all, they'll add up to 100%. I'm just showing you the two biggest. Okay, and then back to the Diels-Alder transition structure to one more time. Let's see what's going on in polarization. In other words, that which should happen as the preamble to charge transfer. We find three significant singular values or complementary occupied virtual orbital pairs, and that reflects the collective response of all 6 pi electrons. And here's one. So this is polarization on the diene, and you can see that this is in fact the diene HOMO polarizing in such a way that it begins to polarize towards the alkene. Again, the phase convention guides us to interpret. And then the second most important polarization contribution is on the alkene, and you can see it begin to polarize towards the diene. And also look at the interesting way in which the double bond is beginning to weaken in the polarization in order to prepare for bond making. And there's the third most. All right, one thing just for fun. Recently there has been claims about a genuine quadruple bond between calcium and fluoride. A visitor to my group, Marcus Weiss, worked on this problem. The binding energy is 308 kilojoules per mole according to CCSD parenthesis T. So this is a very strong non-bonded interaction. And the evidence for quadruple bonding, well, let's just see if our ALMO EDA can support this idea. First, we need to pick a density functional. We struggled with this a bit. We have eventually picked the Hartree-Fock density functional because look, it reproduces CCSD parenthesis T. We had all kinds of delocalization error problems with other more, normally better functionals. But maybe Hartree-Fock is reasonable. The long range, if you put calcium and fluoride a long way away, it's definitely just a polarization interaction. But what happens is you bring them together to the equilibrium geometry to have this 300 kilojoule per mole interaction. Is this, what kind of a signature of bonding do we see? Now, here's the potential energy curves, if you like, the adiabatic and vertical analysis. So there's the frozen interaction, quite weak. So you get only 1/6 of the bonding at the frozen level. So permanent electrostatics is not much to do with this. It doesn't do enough to overcome Pauli repulsion. But look how close the polarized curve is to the full curve. So this is, and there's your vertical EDA. The vertical EDA is dominated by polarization. The adiabatic EDA is dominated by polarization. So at equilibrium, it looks as though this is, in our language, not really a bond at all. It is a very, very strongly polarized system. We would say that for this to be a bond, we need electron delocalization between the fragments, and that is not required at the polarized level. So mostly polarization, not a quadruple bond. Charge transfer only about maybe maximum of a quarter. What about the polarization COVPs? They're quite interesting. A lot of polarization going on the let's make sure I have this right here. Yeah, this is our calcium being polarized by the fluoride, 83%. And again, note the phase convention. This is the S-type orbital of calcium being pushed out into empty space in order to reduce the Pauli repulsion associated with the incoming fluoride anion. And then what do we find for the COVPs for charge transfer? We find 3 of them, and 2 of them are pi type and 1 sigma type. And look at the bonding interaction. So this is making a sigma type bond. This is making a pi type bond in the XY plane, if XZ plane, if Z is the bond axis, and there's another one in the YZ plane. So that's the origin of the quadruple bond. It would be these 3 plus that one. But in our picture, charge transfer is max a quarter and really even less than that. So we shouldn't really be viewing this as a proper quadruple bond. Rather, the charge transfer interaction has triple bond character, the same way that the water-water hydrogen bond has single bond character, but isn't a single bond. This isn't a triple bond. So anyway, so this is finally making a link to chemical bonding at the end of a talk on non-bonded interactions. And so let me try to wrap up here. You may already know this, but if you're coming into listening to this talk and not knowing a lot about the area, this is not a settled area and it's somewhat controversial. And so it's kind of fun to just wrap up in that way. So here's the water dimer again. It's been the theme throughout my talk. And here's this is now, I flipped functionals in order to run a functional for which NBO numbers have been reported. The NBO number for charge transfer is claimed to be minus 37 kilojoules per mole, as opposed to the minus 7 here. So there is a factor of 5 difference to NBO. On the other hand, SAPT is claimed to provide a charge transfer interaction of minus 1.5. So a factor of 5 too big is our number against SAPT, and a factor of 5 too small is our number against NBO. And if you compare these numbers, of course, you have a factor of 25. Well, a normally mild-mannered English theoretical chemist who I've enjoyably drunk tea with that many times when I was visiting Cambridge, wrote in a non-mild-mannered way in 2017 that in its application to intermolecular interactions, NBO provides only a supposed value for the charge transfer energy that is now seen to be worthless on the basis of analysis in this paper. And of course, why should it be considered worthless? Well, let's take this frozen interaction. How can that be wrong? How can it be wrong that we have minus 5 kilojoules per mole of energy lowering at B3 lip when we take the frozen monomer orbitals of the 2 molecules and let them interact? That cannot be a mistake. So the max possible value for charge transfer in our picture would be minus 13.7. And in practice, we think about half of that goes to polarization in B3 lip. So that's why the NBO value is impossible. It cannot be this, because the max possible with this functional is minus 13.7. Even if you think there is uncertainty in the unraveling of that 13.7 between pol and CT. On the other hand, my own former postdoc, a brilliant scientist, John Herbert, now at Ohio State, wrote, the charge transfer contribution has proven particularly vexing to define in a satisfactory way. And he was recommending constrained DFT, which gave 3 kilojoules per mole, which is off from our 7 by a factor of 2 and a bit. Some other definitions afford unreasonably large CT energies, and perhaps this is unreasonably large in those terms. So this is to say that I've tried to outline a theory to you, and it's a well-defined theory, but it is not uniquely defined. And so these are other definitions, and you can see how broad a spectrum of numbers you get. I think we should discard the NBO numbers. I further think that we should discard the SAPT numbers. You can ask me about that later. But yeah, so how do we assess? So NBO grossly overestimates, and I already gave you the argument for that. It doesn't mean that NBO theory is not useful, but you should use it as a descriptor, not as an energy decomposition analysis. And why do I think that CDFT might be too small? Well, it's a real space constraint of zero electron flow. But suppose, for instance, I looked at the formic acid dimer, where I make two identical hydrogen bonds where electrons flow in opposite directions. The CDFT value for charge transfer in this system will be identically zero because left-right and right-left flows exactly match. And so a net population flow constraint is too weak and nature will work around it. And that's why I think that one is not correct. Well, are there any EDAs compatible with what I've told you about, or am I attempting to stand alone? This is a dump. SAP DFT is roughly compatible if one doesn't separate polarization and CT. The BLW EDA is very compatible. It's identical if you use atomic orbitals and not FIRFs. The extended transition state EDA of Bickel, Hoped, and Behrens coming from Ziegler and Rauch is very compatible. Delta E frozen is identical. The orbital interaction is the sum of our polarization and charge transfer. The generalized cone-sham EDA of Su et al., which is implemented in the XEDA code, has an identical delta E froze, and delta E orb in that code is the same as the Bickel-Hoped stuff. So there are plenty of compatible methods. Are we converging? Well, maybe. Maybe. And what I've told you about today is version 2 of the ALMO EDA. It does rely on the correctness or appropriateness of its density functional. So for instance, the calcium fluoride case is a warning against, of the limitations there. We had to choose the Hartree-Fock functional in order to have a suitable one. And it does depend on reference states and paths. But the question is, having made reasonable assumptions, does the value we get from these two apparent limitations outweigh the limitations themselves? I would argue it does. Our host today is a co-author of a paper that points out that EDA methods rely on reference states that have no physical meaning, which is obviously not satisfying from the conceptual point of view. So I can only agree, but try to argue by pushback that we get something that is worth the difficulty of these limitations. And so again, a path function means that EDA components cannot be uniquely defined. So we must live with this. It's a fact. Can we improve on this? Well, that's a question for theorists of a new generation to think about, and it's nice to have good problems to think about, I think. So EDA has a role to play in chemical understanding, design of force fields, data generation for machine learning, and I've discussed variational ALMO EDA with its stable basis set limits for all terms, a nice link to observables, an orbital picture to unravel the individual contributions, and some examples. And then finally, I have tried to own up to controversy where it exists. We are describing non-unique theories, but we should have things that are reasonable. And so in my mind, seeing rough convergence between different EDA approaches and discarding the demonstrably incorrect models can guide us. So NBO should be discarded as an EDA approach because it's demonstrably incorrect. SAP should not, and the BLW EDA should not. And there is probably scope for new work. Anyway, I need to acknowledge the people in my group who turn my rough ideas into concrete reality. Collaborators include Teresa, my partner, Shama Sharada at USC, Pedro Salvador at Girona through Hongsha, Carissa, and Marti. Support from the US and NSF. Our software is in QChem, please try it out if you're interested. And this is my group at away in our Redwoods cabin. And thank you for listening. And finally, I should say that Berkeley time is 10 after the hour. So I was somehow a little late to begin with, but think of it as just Berkeley time. Anyway, thank you.
So thank you so much, Martin, for this quite insightful discussion talk. I'm sure that there will be some questions. We have time for a few of them. Please raise your hands, and I will try to give you to unmute your microphones if you are interested. No. Okay. First, Martin Ram. I think that you can now unmute your mic.
Yes, do you hear me?
Yes, yes,
Okay.
Martin.
Hi, Martin. It's Martin. It's great work, of course. You mentioned towards the end there that, of course, EDA terms cannot be uniquely defined. But I noted in the beginning you mentioned that any good EDA, if I didn't misremember, any good EDA should basically decompose the energy in these terms that you discussed. The historical polarization, charge transfer, and Pauli, and so on.
Well, these are the...
Now, would it not be possible to imagine completely different kinds of terms?
Maybe. So again, I guess kind of coming into this as a sort of pedestrian chemist who hopes that they're a pretty good theorist, I largely wanted to kind of begin with terms that are, they must be right at long distance. In other words, electrostatics, induced electrostatics, CT, Pauli repulsion, etc. They have these well-defined distance dependencies. And so we spent quite a lot of time checking to see that our terms recover the correct distance dependence when we stretch. So in some sense, you could say it's motivated by things like Anthony Stone's classic textbook on the theory of intermolecular interactions, which is essentially, trying to identify what goes on at long range. At short range, one is free to think about different ways to arrange, I think, but one may then have trouble if one wishes to connect to the long range. So maybe the strongest argument for keeping the kind of, let's call them the classical concepts of intermolecular interactions is that at long range, they are the ones we know are operative.
Okay, thank you.
Okay, we have another question from Al. Now you can talk.
Yes. First of all, thank you for the nice talk. This is Alessandro Fortunelli from Pisa.
Okay.
My question is the following. So it's very nice talk. When you use unitary transformations, I mean, that means that you have orthogonalized in some way the basis set on the two fragments. And my question is technical, and isn't it this the most, I mean, the problem, the issue which makes EDA non uniquely defined? So the fact that anyway you define the orbitals on one fragment, when you put the two fragments together, these orbital overlaps and you need to orthogonalize them. Thank you.
Okay, thank you for the question. This is an insightful question and one that deserves more than a short response, but maybe I only have time for a short response, so let's try. So it is true that orthogonalization tails are the origin of Pauli repulsions, and they're also the origin of loss of fragment identity. So for instance, the unitary transformations associated with relaxing the polarized state, relaxing the frozen state to the polarized state, those do not require interfragment orthogonality. that's unitary relaxation on a fragment. So it's just the fragment orbitals that need to be orthonormal in the polarized relaxation. So in that case, in fact, the interfragment overlaps change as a result of doing the relaxation, the unitary relaxations on fragment. And in fact, there is no loss of generality associated with orthonormalizing on a fragment. The fragment space, Hilbert space, remains exactly the same before and after orthonormalization. So I think the polarized analysis, well, I hesitate to say it, but it definitely does not suffer from the objection or the question you're raising. The charge transfer interaction is directly subject to the orthogonalization requirement. So in other words, we can't do that beautiful line integral theory, I think, unless we orthogonalize the orbitals on fragments. And so we do that. The virtual space is simply projected against the other fragments. So if you say, let me begin with the potential acceptor orbitals on fragment 1, what I do is I project out the donor space of fragment 2 when I interact them. In other words, it's just a projection to get those states fragment orthogonal. And so that's what we do there.
Thank you.
I think there may be scope for improvement. In other words, I think I'm very happy with the polarization theory. I'm a little less happy with the charge transfer analysis, and the point you raise is my underlying reason for being less happy there. So thank you for raising it.
Thank you.
Okay, any other question from the attendees? It doesn't seem so. Well, I maybe have one. So I'm interested in how, for instance, SAPT, which is very much used in the long range, all its components transform into other components in other EDAs when distances decrease and we go from the long range to the short range, let's say, limit. That is an interesting question that maybe should be explored a little bit more. Do you agree with that? Do you have any questions on that?
I agree with that. I think that building bridges between EDAs is very useful. And I didn't have time to do it, but we have built a bridge to the ETS NOCV EDA recently that allows actually some improvement in the latter. In the case of SAPT, in my understanding, the main question that is not resolved is how to take SAPT induction and to separate it into electrical polarization and charge transfer. That seems to not be satisfactorily answered. There is another question about the order by order contributions that I don't have a good feeling for, but I agree would be valuable to look at closely.
Okay. In the meantime, there are two other questions. So the last ones. The first is Ralph Toner. I think you can now talk, Ralph.
Yeah, all right. Thank you very much, Martin, for the great talk. You used the frozen energy for good reason, of course. You nicely explained it. And EDA that we are also using has this sort of product state with before the polyrepulsion starts. And if I remember, I think you have a few publications where you did split up the frozen energy term, but if I understand you correctly, then from a conceptual point of view, you prefer to keep the frozen term, although you will then mix up the different contributions. Can you maybe comment a bit on that again, on your view on splitting this up versus not splitting it up and then mixing the contributions?
Sure. Thank you for the question. And it could be there is room for more work here. In other words, what I say may reflect my own limitations. So in my view, the nicest thing about the frozen interaction is that it's a valid, quantum mechanically valid trial state. And so it gives a variationally valid energy. It's just that that energy comes as a package, as we've said. The reason for not wanting to separate it then is that if I were to pull out, for instance, just the electrostatic term, I would not have something that is characteristic of a variational trial energy. Rather, I have a very big, potentially very big and negative contribution to maybe a small frozen energy lowering that might be almost exactly counteracted by a very big and positive Pauli repulsion. And EDAs get into trouble when components get big. So the simplest reason for liking the package of the frozen interaction is that it puts a bound on the magnitude of the interaction. It doesn't get so big. And that makes it a little easier to think about. Giant canceling contributions are not likely to be very insightful, I don't think.
Maybe
But
if I can quickly follow up,
Yep.
Angel.
Yes.
Thank you.
Sure.
Yeah, of course, the big number argument is of course always one towards this analysis, but we like to discuss the Pauli repulsion, or many of the practitioners in the field, in terms of steric repulsion. Can you comment on how would you can you discuss the concept of steric repulsion with the energy terms that result from your splitting up? I understand all the arguments.
Yeah. So okay. So I mean the it comes out beautifully in systems where we might say we expect the electrostatics to be not very important. So if we simply ask what is going on with the frozen interaction when we push two noble gas atoms together, we get a picture that makes a great deal of sense. And that is that, if we say, well, the net package here has no meaningful electrostatics, the energy rises strongly, and it's a result of the induced ripples or nodes in the wave function. So we have kind of a picture. There might be scope for trying to actually look at the fragment frozen orbitals, which should then show that we've tried to do that a little bit. They should show the wiggles and the ripples that kind of create space in between molecules where density would otherwise have been, but that would be Pauli exclusion violating. So you get kind of this push away, and then polarization can either accentuate or recalibrate that. So yeah, not a terribly satisfactory answer, I fear. Maybe there is scope for more work there. We should actually be pleased to see where there is scope for more work.
Thank you.
Okay, and finally, Gernot Franking, I think that you can now talk.
Yeah.
Yep.
Yeah, I have a question. Your ALMO EDA and all other present commonly used EDA approaches are based on density functional theory. What about methods which use correlated ab initio methods? What do you think about the possible development to have such methods? It would be good to have a highly an EDA which is based on a very accurate, highly correlated ab initio method, which could be used as a reference for the DFT-based approaches.
Thank you. That's a very important comment, and it's absolutely correct. In other words, I 100% agree with that, with the desirability of this. I might quote the famous quantum chemist Nick Handy, who I remember Nick standing up in a Sanibel conference in the early later 1990s to say that my entire group has stopped doing wave function theory because the algebra is too difficult. We are now henceforth only going to do density functional theory. So the only objection is a practical one, which is that it is difficult to do this. So my group has I have been working on a project in linear scaling correlated methods. I'm trying to seek an alternative to DLP&O. And as a result of that project, we just published in 2025, early this year, an MP2 and regularized MP2 energy decomposition analysis built on the ALMO framework. It was difficult to do it and quite complicated, but we did succeed in making frozen, polarized, and charge transferring contributions. I would also point out the work of Bistoni and Neza on correlated EDA. That work does not clearly separate polarization and charge transfer, but again, it's a technical problem. How do you do it? It's quite difficult. So there is a little bit of progress in this direction, but the work is difficult. So I think your point is a very good one, and we are just held back by the algebraic challenges of high-order couple cluster theory.
Okay, so
thank you.
Okay, so I think that with this, we have to thank again Martin for this very nice presentation. This is the end of this first lecture of our series, and I want you to take a look to our web page. I don't know if you can see now the information which you can see in the screen. I hope so. Otherwise, you have it in the chat of this lecture. And with this, I will finish. We will announce the next lecture of the series in a few in a month or so. So thank you all of you to have attended this session, and that's it. Thank you very much. Thank you, Martin, again. So this is it.
Thank you for the invitation, and it was a pleasure.
Okay. Bye-bye.